Today I'm going to discuss linear independent and linear independent vector space. Okay, a linear vector space consists of a set of vectors or functions, the standard operations, addition, subtraction, and some multiplication. So subtraction and scalar multiplication to in the solving ordinary and partial differential equations. We assume that the solution space behave like an ordinary linear vector space. The primary concern is whether or not we have enough of the correct vector space needed to span solution the space completely. Now we investigate these notations as apply directly to the two-dimensional vector space and the differential equations. Okay. So here I'm taking the very familiar two-dimensional equivalent space. So the two-dimensional equivalent space is this a familiar x comma y plane. The two standard vectors in the xy plane are traditionally denoted as I and j. The vector I is a unit vector along the x-axis and the vector j is a unit vector along the y-axis. Any point in xy plane can be reached by sum of linear combination and the superposition of these two standard I and j vector. Then we say the vectors span the space. So that fact the only two vectors needed to. So the fact that only two vectors are needed span the two-dimensional vector space. It is denoted by R2 is not coincidental. So here I'm taking two vectors. This one is one vector and another vector this one. The two non-collinear vectors on a plane are a linearly independent vector space. The best example is a well-known xy plane equivalent two-dimensional vector space. Okay. So in mathematical form, we can express like this. So for example, if I take the set of non-zero vectors, now you can understand the better way after explaining the mathematical set of n non-zero vectors uh, like phi 1 and phi 2, and so on phi n is said to be linearly independent if and only if the solution of the equation. So here I'm taking psi multiply with some base I1 and A1, A2, I2, plus and so on plus AN and sorry, IN equal to 0. So here A1 equal to A2 equal to A3 equal to and so on equal to AN equal to 0. Then we call that vector space linear independent vector space. Okay. Otherwise, if this base is A1 and A2 and this constant equal to and so on equal to AN not equal to 0, then we called the type of space linear dependent vector space. So I can explain in simple manner linear dependent vector space. So if I take one vector here like this one is vector A, and vector B also is there like this one is vector B. So I'm going to add this combination vector B and multiply some constant value, which means some k or anything alpha beta gamma some constant k into A. So this type of uh, vector space is called a linear dependent vector space. So whatever we discuss here, there are two planes, two uh, non-collinear vectors on a plane are called a linear independent vector space. This is a x and this is y. These non-collinear vectors are called linear independent uh, vectors. So for example, I can explain by using general example using mathematical way. So, so we know Rank-Skin differential linear independent wave equations determinations. So here I'm going to write this Wronskian, the linear independent determination. For example, W is a function of u comma v. So here I'm going to write these functions like this. By using this rank scheme, we can find out whether given vector space is linear independent or linear dependent. In case x, y, z axis are there, then w, u, v, small w. So then we can write this equation u, v, w. So u first derivative, v first derivative, small w first derivative, u double derivative, v double derivative, w double derivative. So then we can do some determination d equal to a1 and a2, a3, or we can take like this. This one is b1, this one is c1, and a2, b2, c2, a3, b3, c3. The determination of this thing d equal to, can write, if it is comes to 0, then that is one is the linear dependent one. Determination of this function will become linear independent. So not equal to 0. It is come not equal to 0, then we can call that a linear independent vector space. This linear independent vector space can express in terms of linear combinations of the wave equation. I mean linear combinations. So let us check the following the examples. First example, here I'm going to explain the first example. So 4 comma x comma e power 2x is there. Now I want to check this one is whether it is linear independent or linear dependent. So we can write the function w is a function of u comma v comma w. So this one is 4, this one is x, is equal to x, right? X, y, z. So see here, the first derivative is the second derivative is there with respect to these functions. This is the 4, this is the v is the x, w is 2x. So I'm going to differentiate these things. This one is here one time I'm going to differentiation this one. I got 0, one time x differentiation, 1 time this differentiation e power 2x, e power 2x into 2. So again I'm going to differentiation these things. Here 0, this one is 0, and 4 e power 2x, right? So here I'm following this Wronskian differential determination, right? So this is the linear independent. Whether the vector space is the linear independent or dependent, we can check by using this Wronskian function. Okay. So what is the determination of this function? So 4 into, so these are all 0, only remaining 4 e power 2x. So that is equal to 16 e power 2x, right? So this is the linear independent. So determination is not equal to 0, then it is come to the linear independent. And another example is, so example 2, check this function x comma 5x comma x square is a linear independent or dependent. Okay. So first write this Wronskian function, the determination. This one is x comma is 5x comma this one is x square, right? So then one derivative x derivative 1, this one is 5, this one is 2x. Okay, one is 0, again derivative, this one is 0, this one is 2. So determination of this function equal to 10x minus 10x. So that is equal to 0. So this is the linear dependent vectors. Linear dependent vectors. Okay. For example, we know the definitions of linear independent and dependent, right? See here. So the set of vectors here we can take pi1 and pi2 up to pi n is said to be linear independent if only the solution here the base is a1 and a2, whatever you call the a1 a2 bases or scalars, a1 is equal to a2 is equal to and so on, n is equal to 0, then we can call that function linear independent wave equation. If it is not is equal to 0, then we can call that function linear dependent equation. Okay, so and again I'm going to explain one more example. So let us take third example. 6 comma minus 9 0 minus 2 3 comma 0 is there. So here this one is ijk, this one is ijk, right? So I can write this equation in terms of definition of a1. So I can write like this: a1, this one is pi1 plus a2 and pi2 plus and so on plus an in is equal to 0, right? So this is the a1 into 6 comma minus 9 comma 0 plus a2 into minus 2 comma 3 comma 0 equal to 0. So this one is I j k, this one is I j k, right? So 6 a1 I 9 a1 j cap plus 0 a1 k cap plus uh, minus 2 a2 I cap plus 3 a2 j cap plus 0, be careful here, a2 k cap is equal to 0. So here I got 6 a1 I cap minus 9 a1 j cap minus 2 a2 I cap plus 3 a2 j cap equal to 0. So here I cap is there, here I cap is there. 6 a1 minus 2 a2 I cap plus 3 a2 minus 9 a1 j cap is equal to 0. 6 a1 minus 2 a2 is equal to 0, then a2 is equal to 3a1, right? What is this mean? So this is the linear dependent. If a1 is equal to a2 is equal to a3 is equal to I got 0, then we can call that equation linear independent wave equation. So here a1 a2 is not is equal to 0, then we can call this linear dependent vector space. Okay, so why this linear independent dependent vector space is important in quantum? For the given vector space V, uh, let us say here, so set of, for example, if I take the set of vector space pi1 and pi2 and pi3 and so on pi n. Okay, so this is the given vector space. The maximum set of linear independent vectors are called bases. The maximal set of linear independent vectors are called basis of the vector. This is the basis meaning. So I can say in other words, the basis of the vector consists of a set of maximum possible number of independent vectors that belongs to that space. The basis of the vector space consists of a set of maximum possible number of independent vectors that belongs to the space. So here the psi1 and psi2 and so on psi n to be denoted some shortcut here the psi is called basis of the vector space. Okay, and next important word is dimension. What is dimension? So in physics we can call three-dimensional, four-dimensional, five-dimensional, six-dimensional, the array and tuple, infinite dimensional, finite dimensional. So what is dimension? So the dimension of vector space is given by the maximum number of linear independent vector space that we have. That is called the dimension. First, I'm going to write here the definition. The dimension of a vector space is given by the maximum number of linear independent vectors the space can have. Okay. If the maximum number of linear independent vector space has n, so then we can call that n-dimensional space. For example, if we take psi1 and psi2 and so on psi n, then we can call this n-dimensional space. If set of vector consists of the, for example, psi1 and psi2 and so on, sorry, psi3, psi4, then we can call this one uh, four-dimensional or four-tuple um, four-dimensional space. Or sometimes we can call this the name n tuple, five tuple, six tuple. Okay, not going to discuss that thing here. So this is the four dimensional. In case if it is consist of only the three, then we can call three dimension. So these are all the what is linear independent vector, linear dependent vector, what is the basis, and what is the dimension. Okay. Then finally, I'm going to discuss with you the what is the inner product of the two vector. So that is very important. So for simplicity, I'm going to take here the two-dimensional vector space. Okay, the two-dimensional equivalent space. We can say that x comma y. The linear independent can be geometrically understood to meaning that the two vectors do not um, lie. So sorry, do not lie along these same directions. Okay, that is the we already discussed that thing. So which means this is the one, this one is another direction. This type of thing we can call non, for example, this one x-axis, this one is y-axis, xy plane, non collinear. The non collinear vector space. Okay. So in fact, any set of two non collinear vectors could not also be span the vector space of a xy plane. There are an infinite number of set of vectors that will do the job. So the one common connection between the all the sets, however, it is that all the sets can be show the linear independent. That is the all the set can show the reducible to the linear combination of the standard um, unit vectors. For example, I and j vectors. The two vector sets. Here I'm taking two vectors. So the two vectors. So S1 I say the S2 two vector sets I plus j comma 2I minus 3j are both linear independent set of vectors that span the two-dimensional x comma y space. So here one note that the vector within the each set are linear independent. but the vectors between the sets are the linear dependent. So a set of vectors are linear independent that span space, it is called the basis also. Okay, so here I'm discussing inner product of the two vectors. Very important this one. Inner product of two different vectors So let us take one vector space. So this one is the u vector, set of vectors here u1 comma u2 comma u3. So another vector v, this is v1 and v2 and v3. Then the inner product of these two vectors is given by inner product of the uv is given by u1 v1 plus u2 v2 plus u3 v3. Thus the inner product is the sum of the product of the component of the two vectors. The inner product is sometimes also referred as the dot product. If you take the square root of the inner product of the vector itself, then we are called the length of the vector. Commonly it is called norm. Okay, so the norm of this vector can be written like this: inner product of the u comma v. So for different different vector space have different inner product. For example, we consider the vector space. So if here I'm taking another example, the inner product very important. Vector space, all the functions that are continue over the finite closed interval between a and b. Let the function f of x and g of x, two differential vectors in the space. The inner product of these two vectors over the interval with respect to the weight function is defined by the integral. The inner product f of function integral a to b f of x and g of x and wx dx. So weight function here, the wx is a weight function. Okay, from the basic definition of the definite integral, we see the inner product to be the sum of the product of the component of two vectors. So similarly, in the space of continuous function, if you take the square root of the inner product of the vector itself, then we can evaluate the length or norm of the vector can be written like this. So this norm is function square root of a to b wx dx. So this is the inner product of the vector space. So whereas come to the our quantum mechanical case, so generally we can observe this type of functions. There are example quantum mechanical case, the inner product, two vectors. One is psi n of x, another one is psi m of x, which are indexed by the positive integers n and m are the orthonormal with respect to the weight function over the interval a to b if the following relation holds. Psi m of x, wx and dx. So delta n comma m. So here delta n comma m is a familiar Kronecker delta function whose value is 0, whose value is 0 if n not equal to m, whose value is 1 if m equal to m. Orthonormal sets play a big role to development of solution of the partial differential equations in the quantum mechanics. So this is all about this lecture. So here we discuss uh, only four basic fundamentals. One is what is a linear independent vector space and the linear dependent vector, and what is the basis, what is the dimension, how uh, this linear independent vector space can check by using whether if a given function is linear independent dependent by using Wronski linear independent differential functions formulas, and inner product of the uh, two vectors. In case we have the two vectors, how we are going to write this inner product of the two vectors? These are the examples of the inner product of two vectors. Okay.